Welcome everyone to your final day of Calc BC notes. We will have a test on Tuesday of next week, just so we are clear. I am also going to modify the test review. I will post that as well, probably with the message that you use to get this document in video. So that should be there for you to look through some things as well, some different types of problems. What you'll see today, every single one of these, usually what the second or third day we would do these with in class, I just print out a bunch of old free response questions. This is 100% of the time a question on the AP test for you guys. It's always the very last question is the sequence and series question. I would say before this year, it's 100% chance that you would get one. There's never been a BC test where there isn't a sequence and series question. Even this year, I'm willing to bet there's like a 95% chance that this is going to be one of your two questions. If it isn't one of your two questions, I'm going to be a very, very furious Mr. Pena for them making us teach this to you online when we're not in front of each other, and then they don't even test you on it. So again, my whole belief is they made us do this because this is going to be one of your questions. So you're going to see all these different questions here. A lot of them I had to kind of edit because we haven't had to learn everything in this chapter. So every single one of these is at least a part of a free response question, if not of an entire free response question from past years. So here we go. The Taylor series about x equals 5 for a certain function f converges to some function for all x in the interval of convergence. The nth derivative at x equals 5 is given by, and then they're giving you this formula here to figure out what our derivative is. And then they tell you that f of 5 is equal to 1/2. Then they're asking you, at least this was our part A in this question, and then there's the follow-up parts to this question are just things we haven't learned. All we have to do for us is write the third degree Taylor polynomial for the function about x equals 5. So our third degree Taylor polynomial. So again, if we're going to write this as a polynomial using that p sub 3, that's fine. You can use your equal sign because that's truly what we are finding here. We are finding the polynomial. And that's what P stands for. So this is our polynomial. Since we're using that to approximate our function, if you want to write f, then you would say we are approximating our function by using the polynomial. So whichever one of these you're going to use, that's fine. I think for this one, I'm probably going to do the polynomial. That's all it's asking us to do. Write the third degree Taylor polynomial for our function about x equals 5. So I'm going to go with that notation. What we would hopefully know at this point is the first term in a Taylor series is your functional value at wherever we are centered at. We are centered at 5. They just flat out give you that value. Our first term is a 1/2. Plus, actually, let me just write all this out now so we understand where this is all going to come from. We then want our derivative at 5. And then we would have x minus 5 to the first power over 1 factorial. Then I would want the second derivative at 5, x minus 5 to the second power over our second factorial. And then our third derivative at 5, x minus 5 to our third power over our third factorial. Third degree, again, means we're going to when we have a power of 3, whatever that term would be. So from this, we know our functional value is a 1/2. To get these derivative values, really the only missing element right now that we have, this is pretty much our answer that we have written up at the top. We just don't know what these values are. If we know those values, you're just plugging them in for those spots, and that's pretty much going to be your answer. So that's what this was given to you for. This is how we're going to figure out our derivative. So if I want the first derivative, so we come up here, what that tells you is your n is going to be a 1. So wherever we have a 1 in this formula here, you are plugging in, wherever we have an n in that formula over on the right-hand side, you are going to let that n be a 1. So for this one, we would do a negative 1 to the first power with a 1 factorial, all divided by 2 to the 1, and then 1 plus 2. That's your derivative, and then we would still have x minus 5 all over, and then x minus 5 to the first power all over 1 factorial. So that was our first derivative, first power, first factorial. For the second derivative, what that would now mean, since we're doing our second derivative, we would now have n equal to 2. Same process, wherever we have an n on the right-hand side now, you're going to plug in a 2. So that would give us a negative 1 to the power of 2, a 2 factorial, a 2 raised to the 2 power, 2 plus 2. That's our derivative value. We'd still have x minus 5 to the power of 2 all over a 2 factorial. Last one, if n is a 3, or if we're finding our third derivative, if that's what we want, our n here has to be a 3. So now you're going to have a negative 1 to the power of 3. You're going to have a 3 factorial, 2 raised to the power of 3, 3 plus 2. Then we would have x minus 5 to the power of 3 all over our 3 factorial. Believe it or not, if that's all they were asking you to do, they would take that. You may want to clean this up, but that is an acceptable answer. So if you are scared, even if you read through that document I had linked earlier in a previous message, you'll see they actually tell you don't get too worried about simplifying this. I'll go through it just to make sure we could. And again, we probably won't even simplify it as much as we could, but let's just make sure we understand what this is going to be. This would have been negative because we had the negative 1 to an odd power. And then we would have had a 1 in the numerator, and then we would have had, what, a 6. Well, let's do 1, and then x minus 5. And then we would have had a 3 times a 2 in our denominator, so that would be a 6. Signs are now going to change to a positive because we have the negative 1 squared. This 2 factorial would cancel out that 2 factorial, so those would go away. We would then just have an x minus 5 squared. Our denominator is what? 4 times 4, so 16. Third one, going to be back to being negative because we have the negative 1 cubed. This 3 factorial, that 3 factorial are going to cancel. So we would just get x minus 5 cubed here. Clean this up a little bit for you. And then what we would be left with is an 8 times a 5. So we would end up with a 40 in our denominator. And then that's it. That's our Taylor polynomial of third degree. They're very clever with things they're going to give you. You have to, again, be able to think on your feet a little bit here in a couple of weeks when they throw something at you that's a little bit different than what you've seen before. All right, this one now was a full-blown question. If I remember correctly, did I give you all? Well, not quite, but it's going to give us a few of them. So you're given a big table here, a bunch of values for x, and then h's and every derivative that we would want through 4. Then it tells you that h is a function having derivatives of all orders for any time x is greater than 0. Selected values of h and its 4 derivatives are indicated in the table above. The function h and the 4 derivatives are increasing on the interval from 1 to 3. 1 to 3, that's pretty much where we're looking at. So letter A, write the first degree Taylor polynomial for h about x equals 2. That should be pretty quick. You're going to use that to approximate h of 1.9. And then you're going to identify, is this approximation greater than or less than h of 1.9? All right, so first degree Taylor polynomial, we'll do p sub 1 of x. Since we're going to be doing this about the x value of 2, we're going to be using the second row here. We would want our functional value at 2. So here's 2. Here's our functional value. Then we would want our first derivative value at 2. So that's 128. We would have x minus 2 to the power of 1 over 1 factorial. And no, you do not have to write both of those, but just so we understand the formula, that's where we would assign those values. So p sub 1 of x is just 80 plus 128 times x minus a 2. You are now going to use that to approximate h of 1.9. So notice I'm just using an equal sign here because this is our polynomial. That polynomial is an approximation for h. So for me to now use this thing to approximate h of 1.9, I'm going to say h of 1.9 would be approximately 80 plus 128, throw in your 1.9 here. And that should give us h of 9, or h of 1.9, should be approximately 67.2. So that's our approximation. Then it asks, is this approximation greater than or less than h of 1.9? So if we knew the real value of h of 1.9, because again, this is an approximation, that's why we're using that symbol. If we knew what this was, which we don't, so there is no magical way for us to come up with h of 1.9. We don't know what that is. All we are given are values between 1 and 2. But it's asking, if we knew what that was, how would that approximation relate to this? So what this gets into, we talked about this with line tangent, we talked, really it's what we have here, and we talked about this with Euler's method. If I'm given a curve, and we have a line tangent to that curve, they share a point here. But if my graph is concave down, every other point on this line would have a value that is bigger than the curve. If I put my point right here, where we're concave up, and I draw a line tangent in, they share a point right here, but every point on this line is going to be less than the curve around that area because we're concave up in this interval, you're concave down in this interval. So if we look at what we were dealing with, this is a line. So our polynomial is a line, and we were tangent to the line at x equals a 2. We knew at x equals 2, this was our y value, and then we knew what our slope was. So this is nothing more than a line tangent to our graph at the x value of 2. They tell you that h and the 4 derivatives are all increasing. So that means not only is our derivative, or our function increasing, but so is the derivative. So that tells us we are concave up. And also, if we look at our table here, if we're always increasing, there's no tricks with this. At x equals 2, we can look at the second derivative. I guess we only really need that middle term, so let me focus in on that. Notice how our second derivative is positive. That would tell us also that we are concave up. But the fact that h prime is always increasing means the original function is always concave up. So since we are always concave up, any line tangent, once we get off that point of tangency, the value on the line, which is what we just did here, we used the line to find this value, the value on the line would be less than the real value of the curve. So this would tell us that our approximation is less than, because h of x is always concave up. Therefore, our tangent line would have a value, let's do a value, yeah, under the curve. Okay, something to that effect. Basically, just explain, we have a tangent line. The tangent line, if you are concave up, is underneath our curve. Therefore, the line value is going to have to be less than the actual value. We will get into that more too. That's a review coming up with Euler's method, and we'll revisit that idea also. All right, so make this a little bigger so we can use our table to do letter B. All right, letter B is again asking you to look at x equals 2. You're now going to write a third degree Taylor polynomial, about 2, and then do the same exact thing. We're going to approximate h of 1.9. We just did that up here, but the whole theory behind this is the more we include, the more accurate our approximation would be. So if this is a first degree polynomial, when we do a third degree Taylor polynomial, it should be even more accurate. So we would say our third degree Taylor polynomial starts out pretty similarly because we're still dealing with 2. So we're going to have 80 again. We would still have the 128 times x minus 2 to the power of 1 over 1 factorial. The second derivative value is 488 over 3, x minus 2 squared over 2 factorial, so that's our second degree. And then our third degree is 448 over 3, x minus 2 to the power of 3 over our third factorial. So that's our third degree Taylor polynomial. We're now going to use that to approximate that value again. So our functional value for h at 1.9 should be approximately, and then we're just plugging, wherever you have an x, we're going to be plugging in a 1.9. So here, here, and here. So if you want to write all that out, that's fine. But we're plugging all that into our calculator. Okay, there we go. Try and move that up. Should give you 67.988. Should have been in the same ballpark. So here was the first one. Here is our second one. We would know that this is now more accurate. Should make sense. If we knew this was smaller than the real approximation, so that means the real value was greater than 67.2, this should be more accurate because it's bigger than our approximation, and we knew we needed to increase to get to the real value. All right. Okay, next one, number 3. Interesting one here. This one that I definitely want you to see, part A. And see if you remember what this is. A function f is defined by, and then you're given the function. So you're given the first 3 terms, then you're given the general term here. And then for all x in the interval of which they would be converging. So letter A, I would probably have you try this here to see if you know what to do. This is part of this chapter. It's not specifically a sequence and series topic, but it is something that we have done in this chapter. If you want to try, see if you can figure this out, feel free, pause me, try it. I will go on. This is a limit problem. So any limit, your first option is to try and substitute. If substitute doesn't work, then we would try to simplify. And then the third way we did this is with an XY chart. We now have a fourth way of doing this, and that is called L'Hopital's rule. L'Hopital's rule, though, will only work if you get a 0 over a 0. So lo and behold here, think about what would happen. If we do this first option and we substitute in, we would get f of 0 minus 1/3 over a 0. So here is f. So think about what f of 0 would be. So if I'm going to let the x be a 0 here, if this is a 0, this is a 0, the next term would have had an x cubed, the next term would have had an x to the 4th. All of these are going to have zeros in them. So that means all of these are going to go away, and the only thing you would be left with is a 1/3, and then we subtract a 1/3 over our 0, and lo and behold, you get a good old-fashioned L'Hopital's rule problem. All right. So we substituted, we get 0 over 0. That allows us to do our little shortcut using our derivatives. So that's our next step. Yes, buddy?
He'll find us when I need to tell him something.
All right, hold on.
And I said all around the house. And he wasn't anywhere around the house. All
right, so then, that was Isaiah, everybody. So then now we take our derivative. So the derivative of this would be f primed of x. The derivative of 1/3 would be 0, so we really just have a minus 0 here. So we'll have to show that. Your denominator's derivative would be a 1. So if we go back to what f is, so let me now get rid of all that mess. Think about what happens if we took the derivative of this, which we've now done a little bit. It's an algebra idea. Whatever we do to one side, we can do to the other. This would give you a derivative of 0. The derivative of this would leave you with a 2/9. The derivative of this one, you'd multiply by 2. So you'd get 6 over 27, x to the 1. After this, there would have been an x cubed term here. Whatever that would have been, if we would have written it, doesn't really matter. We would have taken our derivative, there would have been an x squared. The reason it doesn't really matter is because what we're ultimately trying to figure out is what happens as our x becomes a 0. So this term still has an x. This term would have had an x. Every term after this would have had an x in it. X cubed, x to the fourth, all that good stuff. So these would all be dropping out of our derivative when we let our x's become a 0. The only thing we would then be left with is a 2/9. We only have a 1 in our denominator, so that limit is 2/9. Not uncommon. They like to throw in a little L'Hopital's rule. That's a BC specific topic only. It's not something the AB, well, actually, I guess they know that for this year, but that's a really common question with these also. All right, B, similar to some of the ones that we've done, write the first 3 non-zero terms and the general term for an infinite series that represents the integration of f, keeping in mind, let me again clear some space here, keeping in mind that f is the function that you were given above. Notice again, just make sure we're clear, they're using an equal sign. The reason they can get away with that is they're given the general term. It's the only time we could use f is equal to if we can provide every single term, and the only way to provide every single term is with the general term. So what we're going to do, though, we want the first 3 non-zero terms. So we're going to set up this problem 0 to 1. We want to do f of x. So if we want the first 3 non-zero terms, we're going to have our 1/3, our 2, I'm going to go ahead and simplify this, 2/9 x. And then over, think about what this would be. It's 3 over 27, all right, which is 1/9. And then x squared. So just a little derivative or antiderivative idea. We'll do 1/3 x plus 2/9 x squared. And then we're going to divide by 2. Plus 1/9 x cubed divided by 3. We're going to evaluate that from 0 to 1. Put in your upper limit, so let all of your x's become a 1. So this term would become a 1/3. If you notice what happens in the second term, these guys would have canceled, and we would just get a 1 squared over 9, so 1/9. Over here, we would plug in your 1, you would get a 1 over 9 times 3, which is 27. That's your upper limit plugged in. Minus, throw in your lower limit, they all have an x, so our lower limit would just yield a 0. So they're asking us what's the first 3 non-zero terms and the general term. Our first 3 non-zero terms would be 1/3 plus 1/9 plus 1 over 27. And then we want the general term, so we would do plus and then dot, dot, dot. And then we need to identify what that general term would be. What we would know for sure is there's going to be a 1 on top. And then hopefully we can recognize here that we have 3, 9, 27. So that's 1, 3. And this is 3 times 3. This is 3 times 3 times 3. So we really have 3 squared, 3 cubed, so on and so forth. So then your question sort of is, where do we want to start this? We're clearly going to have an exponential function with a base of 3. Would we want n, or do we want an n plus a 1? Because this would work if our n is a 0. Let me put the little sigma sign out there so you know what I'm referencing. So it's an infinite series. If we start at 0, we would look, does that actually give us our first term? And it wouldn't, because we would want our denominator to be a 3. And if n is a 0, you're going to get your denominator to be a 1. But if I make an n a 1, that's where we start, then it will work. You would do a 3n. So the question is sort of which one do we want? The way we would know that is we want to go back to the original series and identify what that one was starting at. I mean by that, if we go back to the original problem, look at the general term here and identify, how did we get 1/3? What was the n equal to make sure that our first term was a 1 over a 3? And the only way that that would have gotten us a 1 over a 3 if n is equal to a 0, because then you would get 0 plus 1 would be a 1, x to the 0 would have been a 1, In your denominator, you get a 3 to the 1, which gives us that denominator of 3 that we were wanting. So the fact that the original one starts at 0, the one that we are basing it off of, that means our new one better start at 0. So since this has to start at 0, because that's where the original one starts at, in order to get a 1/3, a 3 in our denominator, we would have to do this as 3 to the n plus a 1. C then, find the sum of the series in part, this should say in part B. So now we want to find the sum of the series that we just did up here. Be careful of this. When I first did this problem, I kind of made this little mistake, and I just found the sum of these first 3 terms. I'm kind of keying this up real quick. But notice what this is asking for. We want the sum of the series. The series means all terms. The series is everything. So we don't want to just add these first 3 up. We want to add every single term in this infinite series. So what this gets into, this is our geometric series idea. Notice how we're multiplying by 1/3 over and over and over and over again. So the sum of a geometric series is the whole little first term divided by 1 minus our common ratio. The first term in this instance is 1/3. And then we would have 1 minus our common ratio. Our common ratio is also a 1/3. So we would end up with 1/3 divided by 2/3, giving us a sum of 1/2. So a little bit of everything in this chapter here, at least some more than just always a Taylor series. L'Hopital's rule in part A. B is, here's a series. If we do a derivative, antiderivative, we just do it to both sides for the function or the series that represents the function. And then we got to remember our geometric series. 4. Function f has a derivative of all orders for all real numbers of x. Then you're flat out given these values. So for part A, the first part should be, both of these parts should be pretty simple. Third degree Taylor polynomial. So p sub 3 would equal, and then these are all the values that we would know in order to write this out. Functional value is a -3. Then I would want my first derivative value of 5. We are centered at 2, so we do x minus 2 to the first power. First factorial. Second derivative is 3, centered at 2, power of 2, 2 factorial. Third derivative would have been a -8, x minus 2, power of 3, 3 factorial. That is in our polynomial. We use that to approximate values for f. Go in, wherever you have an x, let your x's be 1.5. So again, I'm not going to show all that. Hopefully we understand all of these x's, then you plug in a 1.5. When we do that, you should end up with a -4.958. B, write a third degree Taylor polynomial for p of x. And p of x is going to represent g. And g is taking our original function and writing it as a composite of x squared plus 2. And we're going to be centered at 0. And then use p to explain why g must have a minimum value at the x value of 0. So a lot of stuff in play here. So we want a third degree Taylor polynomial. Actually, as I read this now, you're going to need to change this. Otherwise, it's not going to come up with that. So instead of third degree Taylor polynomial, write this in as a fourth degree Taylor polynomial, please. Then this will work out better. So p sub 4, the way we're going to get that, it's going to be for g of x, is by taking the original function, f, and writing it as a composite, or with a composite of x squared plus 2. So this is our original approximation for our function from part A. So p sub 4 of x means we're going to take the original function, so the -3, we definitely would have that, plus a 5 times, and then now instead of x minus 2 to the first power over a 1 factorial, wherever we have an x, our new composite replaces the x with an x squared plus 2. So again, just take this term here, compare them. we have our 5, but instead of x minus 2, the x is no longer a function of x, it's a function of x squared plus 2. We would do the same thing for that next term. So we're going to take this term now, and you would have plus 3, and then instead of x minus 2 to the power of 2, all over 2 factorial, we are replacing our x with our new composite of x squared plus 2. All right, so we've done a few of these where we've taken the derivative of both sides. We've done the antiderivative of both sides. This is now just changing our composite. If I do a composite on one side, we're going to be doing the same composite on the other side. So our 4th degree Taylor polynomial now, see how this plays out, would be a negative 3 plus 5x squared plus, and then notice what's going to happen here. These would also cancel, and then I would get x squared squared. So I'll get an x to the 4th, along with our 3, I guess, over our 2 factorial, which is just going to be 2. That's our 4th degree Taylor polynomial. The next question. This gets into, and this is one of the things that with us not being around, that there's a little more focus on what we're going to do here normally. When it says use P to explain why G must have a minimum value at x equals 0. So this is G of x. All right, G of x is that 4th degree Taylor polynomial. We're using that to approximate G of x. So what this gets at, typically the way we've done these to find minimums is take your derivative, set it equal to 0, see where it's undefined, find endpoints, do your testing, all that stuff. We also did something briefly. We introduced it a while ago. It's called the second derivative test. If we were together, this would have been used a little bit more in this chapter if we had done all these topics, which we don't. But the second derivative test you would be a little bit more familiar with if we were together, because we would have done more of that within this chapter. So what the second derivative test gets at is the idea that if I know my first derivative is 0, there are only 3 things that could happen. So hopefully this is somewhat familiar. We touched on it briefly one day. If my first derivative is 0, that means I could have a max. I could have a min. That can give me a horizontal tangent. And then we also talked about how the cubed graph could level off here. And what that is a point of inflection. So we could have a max, we could have a min, or you could have a point of inflection. Those are really your only options if we have a slope of 0, unless it's just a horizontal line. So what the second derivative test gets at is the idea that, so let me create some space over here. Think about what your second derivative means. If our second derivative is greater than 0, that means we're concave up. If we're concave up at that point, then we'd have to be dealing with a minimum, because not only do we have a slope of 0 here, but our graph is concave up at a min. If our second derivative is less than 0, that means you are concave down. Here is the one that is concave down. So if I know my first derivative is 0 and my second derivative is negative, that's going to tell me we have a max. And then the third thing that could happen is if the second derivative is 0, we don't have any concavity. So at this point, that's where we're changing concavity, and that's when you're going to have a point of inflection. That's what this question is testing you on. That's how we're going to have to approach this. Okay, so if we did this now, take G primed, and then for the derivative, its approximate derivative would be 10x plus 12x cubed over 2. If you want to reduce that, feel free. We're going to do this at 0. Do we have a maximum or a minimum? So let's plug in a 0. And G double primed is going to give us a value of 0. Because G double prime has a value of 0, we know that we are dealing with one of these 3 things. So if we took a second derivative, that would just leave us with a 10, and then we would know the rest of these. We really can use equal signs here because we know this is going to be our functional value. We're getting rid of all of these behind it. All of these would have, we'd have an x to the 4th, an x to the 6th, so on and so forth. But when I now plug in the 0, the only thing we're going to be left with is a 10. put those ideas together that we just talked about over here on the right-hand side. Because g primed is 0, that means we either have, again, a minimum, a maximum, or we flattened out and formed a point of inflection. And then we combine that with the idea that our second derivative is positive, means we are concave up. The only one of these that is concave up is this one, which is in fact a minimum. So this is saying, explain why g must have a relative minimum value at x equals 0. We would say because, I can create a little space here, g primed of 0 is equal to 0. Therefore, g must have a max, min, or point of inflection. And since g double primed of 0 equals a positive 10, let's not use f, it's g of x is concave up at x equals 0. All right. Again, know that that's something that I do feel like there's a little gap right now because we just talked about it briefly. I knew we'd get to it again, at least I thought I knew we would get to it again in these problems, but this is really now the first time we've seen this in this chapter. Okay, if we had done everything again, you would have seen this numerous times. File that away, make sure you can do those. Okay, next one. This might have been last year's question or fairly recent question. And this looks really familiar to me from recent years. So they give you some values. F of 0 is 0, f prime of 0 is a 1, and then they give you f to the n plus 1 of 0, and then they give you the little formula for that. And this will give you another example of just how creative these people are. So you just, again, have to be able to think a little bit, not freak out. No, this is something that you've done, and just apply what you know. So you're given some things here. A function f has derivatives, and then of all orders between -1 and 1, the derivatives of f satisfy the conditions above. The Maclaurin series for the function converges for x for any absolute value of x that is less than 1. A lot of this stuff that you're seeing, I'm really just copying these old questions. A lot of that just deals with some of the items with intervals of convergence that we would have done more of, so I wouldn't freak out too much if you're not understanding fully what that is. All right, let's go through A and think this through. We've done a lot of Taylor series right now. If you wanted to try A, see if you understand what this question is actually asking, you could pause this, see if you can come up with the first 4 non-zero terms. Maclaurin series means we are centered at 0. So you're going to show that the first 4 non-zero terms from the Maclaurin series should be this. So they're kind of giving you the answer. You're just going to show where you got that from. Once we have that, you're going to write the general term for that series. Okay? So if you want to try that, feel free. We're going to dive in here if you're staying with me. So first 4 so let me want to write this. So again, we'll go P sub 4, 4th degree, Taylor polynomial for some x value. Actually, you know what? Since we're going to write the general term, that means we're going to actually write every single term, is what the general term means. So we'll go ahead and use f. So we're going to go ahead and say f of x is equal to, we can do that because we're ultimately writing the general term. And then we need to come up with where all these things came from. Actually, we need to do that first. So the first thing we would need is what's our functional value at 0? That's easy, it's 0. So now I'll write my f of x would equal, and we would do a 0. That doesn't actually count. Terms, we want our first 4 non-zero terms. So the next thing we would need is our first derivative value at 0. That's a 1. So then we would have plus 1. We're centered at 0, so we don't really need to do x minus 0 to the 1 power over 1 factorial. You can just write that as an x. Okay. Plus, we would then want our second derivative, so 2 tick marks at 0. And this is where this gets a little sneakier. This is our functional value. This is your first derivative value. This is going to give your derivative for all values that are greater than 1, which is what we need. We need now our second derivative, we need our third derivative, and we need our fourth derivative. Okay, sorry, and then at 0. So we have to use that little formula. So think about what this now is going to mean. If we want f double primed, so here. So notice how many tick marks we have. If it's a second derivative, then our n, in order for us to use this formula, our n to get f to the second tick mark for a second derivative, the n is actually going to be a 1. So what that would tell us then, in order to figure out what our derivative value is here, we're going to let the n on the other side be a 1. So that would be a -1. And then I would want times the first derivative, because n is again a 1, at 0. So the second derivative at 0 would be a -1 times the f prime value at 0, which we just said over here is a 1. So then we would have a -1. Then we would have x minus 0 squared, so x squared over 2 factorial. So far, so good. All right, just let me finish. So this is going to be our first term. We're all good there, just an x. We now have minus x squared over 2. We now want our third derivative at 0. So if I now want 3 tick marks, come back up to the formula that we are supposed to use. In order to make this a third derivative, then our n would have to be a 2. So on the other side, you would have a -2, and then we would want f2 derivatives of 0. So this would give you, for our third derivative, we would have the -2 multiplied by, again over here, the second derivative value at 0, which we just said was a -1. So f triple primed of 0 was a +2. So we'd come over here, we would have a +2 initially, and then we would do x cubed over 3 factorial. Think about that. That would be 2 over 3 times 2 times 1. So 2 divided by 2's will cancel, and you're just left with a 1/3, like we are supposed to have for this term. Last one, if we want our fourth derivative value at 0, we go back to this tricky little formula up here. If we want this to be a fourth derivative, then our n would have to be 3, so that we would get f to the fourth derivative power. So that means we're going to get a -3 times f triple primed of 0. So that means I'm going to take the -3. I am multiplying it by the third derivative value that we just found over here to be a 2. So our fourth derivative value is a -6. So that's why this is going to be minus. We then do 6x to the fourth over 4 factorial. They would expect you to simplify this when they're saying show how this happens. So now we would go through, simplify this. F of x would equal, this just is x, minus x squared over 2 factorial is really just 2. We mentioned how the 2 divided by 6 basically would give you a 1/3, so x cubed over 3. Minus, this would be 6, and then 4 factorial is 4, 3, 2, 1, so that's going to be 24. 6 over 24 is 1/4, so we get x to the fourth over a 4. We have just found the first 4 non-zero terms that they were asking for if we were to look up here at our original 4 terms. They now want us to write the general term, hence the reason we can say f of x and use an actual equal sign here. So we now want to, try this again. If you want to try to figure out what is our general term, you could try that if you want to take a minute. So to figure out that, this is, again, something to think about. There's a couple different routes you can go here, but only one of them we're going to want to write. Let's say we start at n equals 0, and we want to come up with this set of 4 terms. We're alternating positive, negative, so that's obvious. We know we're going to have this little -1, but since we want to start with a positive value, we would start this at n. So -1 to the 0 will start as positive, and we're going to alternate signs. We would then want to take an x, so all of these have an x to the first, x squared, x cubed, x to the fourth, so we're going to have an x to a power, and our x to the power if we're starting at 0 and we want our power to be a 1, we'd have to do an n plus a 1. Then in our denominator, if we want a denominator of 1 and then 2, 3, 4, and we're starting with an n value of 0, you would need to again do an n plus a 1 so that our first original denominator is going to be a 1. We'll come back to that because we could also do this. We could start at a 1. To make sure we're positive at the beginning, we need a negative 1 to the n plus a 1. We could then just let x be to the nth power, so we get our x to the first right away. And then our denominator would just be an n. Technically, these both give us this, but for our sake, the way we did this, notice how when n was a 0, for us, when we did this up here, and then we would have used that right here, when n is a 0, that's the first term that we do not see. And since that's not what we're dealing with in our function really starts at x, we don't want to go with this guy. We would want to go with what is ultimately the n equals 1 term. That's where this would want to start off at. So we are dealing with, oh man, this guy. Okay. All right, then B, determine whether the Maclaurin series described in part A converges or diverges at x equals 1. So we just wrote the Maclaurin series, we just wrote it. We're going to let x be a 1, so plug x in as a 1. What we would hopefully understand then, that we have a negative 1 to the n. 1 raised to the n is really just a 1 over an n. So now this comes back to all those tests that we had done earlier. What this is the alternating harmonic series, and we would hopefully know that this converges because it is the alternating harmonic series. All right. Okay, last one of these. Write the first 4 non-zero terms and the general term for the Maclaurin series given by, and then you're given this. So this is pretty similar to the ones that we've been doing. G of x is the integration of our function. It's just now of a function of t. So f of t dt. So we'll do g of x equals, and we're going to go 0 to x. We now take that function up above, this guy, write it as a function of t. So we'd have t minus t squared over 2 plus t cubed over 3 minus t to the 4th over a 4 dt. And then now we just execute that. So you'll get t squared over 2 minus t cubed divided by 3. You already had a 2 down there, so that's going to be to the 6, or divided by 6. This would be t to the 4th. We would divide by 4 to give us a 12. T to the 5th divided by 5 with the 4 down there is 20. You're going to go 0 to x. So g of x then is x squared over 2 minus x cubed over 6 plus x to the 4th over 12 minus x to the 5th over 20 minus your lower limit of 0. If all those become 0, then that's just going to go away. So g of x would equal x squared over 2 minus x cubed over 6 plus x to the 4th over 12 minus x to the 5th over a 20. We also want our general term. Now need the general term. Two different ways you can do this. We could try to figure this out by looking at this pattern. That's the hard way. The easy way, kind of the first time we have now done this, and again, I just don't know if this is something that you need to know anymore, but I want to make sure we are covered. Think about what we found up here back in part A. So this general term, this was the general term for this. So what we can really do is just take the antiderivative of this general term. So if we did the antiderivative of this, the negative 1 to the n plus a 1 doesn't change, but do your power rule. You're going to add 1 to the power, so that's going to give us an n plus a 1. And then I would divide by that n plus a 1, and we already had an n in our denominator. That's all we have to do to get our general term. So you're going to have a negative 1 x to the n plus a 1 divided by that n plus a 1 along with the n that was already down there. You can test it if you want, but guaranteed as we now start plugging these in, you're going to get that value. All right. And again, you need to make sure n is a 1 because that's what we started with and the one that was above. All right. This was last year's question. This was last year's question, I think. There's really probably just one I'm going to have you do. Like this, you can't do. Yeah, this is not something that you need to do, so I won't worry about that. And this would be a little redundant. We've done this. But they came back last year thinking part A was hard for some reason. And again, it's just the College Board being creative. So we don't want to freak out when something like this were to happen. They're giving you a function f has derivatives of all orders for all real numbers x. A portion of the graph f is shown, so that's sum of f above, along with a line tangent to the graph at 0. So this is f. This is our line tangent, and they are tangent at the x value of 0. And then selected derivatives of f are given in the table. So you're given, understand what this now is. See how this is your exponent? So what this is really saying, if n is the exponent, what this is really just saying is the second derivative at 2 is equal to, the second derivative at 0, because the 2 is your n is 3. 3 is n. 3 is nothing more than the number of tick marks you would have. So this means my third derivative at 3 is a negative 23 halves. And then if n is a 4, the n is again the exponent for your f. So that's just saying the fourth derivative, doggone it, these are all at 0, sorry, at 0 is equal to 54. All right, so this is just all of our derivative values. And this is the second derivative, third derivative, fourth derivative, and then we are given what those values are. Letter A then asks you, write the third degree Taylor polynomial for f about x equals 0. So my third degree Taylor polynomial is your functional value at 0. We can't get that from the table, but that's why they gave us our graph. Look at the function at the x value of 0. This kind of parabolic graph is your function. And pretty easily, hopefully, we can see that the functional value there is a 3. Plus, we would then want our first derivative value. So they don't give us the first derivative in the table. You have to use the graph. That's what the line tangent gives us. So if we follow this line tangent on down, the slope of the line shares the slope of the curve where they're tangent. So they're tangent at x equals 0. So the slope of f prime would have to be equivalent to the slope of that line. So if we find the slope of that line tangent, so from here to here to here, we're going down to right 1, down to right 1. So our second derivative value is a negative 2. And then we're centered at 0, so we can just, well, I'm going to do it, x minus a 0, and then over 1 factorial, since that was our first derivative, first power. Now we want our second derivative. That's when our table would come in. At the second derivative, we get a value of 3, x minus 0 to the second power, second factorial, and then our third derivative is here, negative 23 halves, x minus 0 to the third power, over 3 factorial. All right? Just a different way of them testing you, making sure you know what you're talking about, okay? So, sorry this got a little bit long. We usually spend a couple of days doing all these old AP questions, so I needed to throw a bunch of them in at once so you can see the different ways that they ask. They're all the same stuff, though, just creative ways in terms of them being asked. If you wanted to try C, feel free. It's something that we've done a number of times. I don't feel like I need to take your time to do it. I think it's last year's question if you wanted to check it. So with that, I'll leave you. I'll leave the test review also on Skyward. And then we'll do our test for those needing to improve their test score. I know a lot of you are in between grades, and it's that one test that is hurting us. So I'll give you that opportunity on Tuesday of next week. I will also probably set up a Zoom on Tuesday of next week in the morning. So if you did have any questions on any of this, you could look at me face to face, and I could hopefully share my screen and answer any questions that you might have. So with that, I'll see you guys later. Have a good weekend, and we'll see you next week.